Okay, engine materials, fasteners, gaskets, and seals. We need to learn about the different types of materials that are utilized in engines, the type of aluminums that are in there, different varieties of aluminum, different alloys and applications, and the different processes. They include stamping, casting, forging, machining, powdered metal, and also CNC printing and EDM, and there's also CO2 laser and a variety of more automated processes that are finding their way into automotive. We have various types of metal processes that happen from the time they take raw material to we get a finished product ready to ship out. And that includes a variety of heat treating methods. Heat treating can be done in an oven, but it can also be done with electrical probes that come down and attach themselves to metal parts. They do that on crankshafts. Crankshafts will have the critical portions of the lobes and the journals heat treated, and you can see that in some crankshafts today that have bluing around the critical parts. There's also types of tempering where we have different temperature ranges. Typically, forged steel alloy is tempered about 1,000 to 11 degrees, called the heat. That is the last process. So you're safe to go about less than half of that, about 400 degrees in an oven if you had to heat it. 400 to 450 degrees in an oven if you had to heat it and do some other processes to those parts. There's annealing, which is a softening process so that materials can be machined faster if they're a little softer and they get more throughput in that manufacturing cell. Okay, there's also case hardening, where just the outside of the part has the temper to it. It's a heat process. And also shot peening, which will remove stress and also material. It's like a BB-sized aggregate that's put a shot against the metal and cleans it and also does stress relief. Methods used to locate cracks in casting. In high-valued things like in aerospace, they'll do radiograph, which is an X-ray. In automotive and truck, we will use our dye penetrant, and we'll use for ferrous metals, we'll be using the mag particle. How to identify, inspect, and get the correct fasteners for engine service. So these are all very important that you know which materials are used, what the processes are, and what you can and cannot do to that part. A purpose of engine gaskets. Gaskets are pretty much for stationary fixed, and seals are for rotating parts. Requirements and construction of head gaskets, different gasket materials, and the application of RTV, room temperature vulcanization sealants. There's several different colors for applications. And a proper application of an anaerobic sealant is like Loctite, which hardens in the absence of air. Due to the wide variety of materials and configurations, we're going to see that manufacturers are going to specify very unique applications. And here, for an example, you have some plugs in the bottom of the sealing across the engine block to the cylinder head. And you're going to see, in this case, semicircular plugs are utilized in this application. So you have to know exactly what the manufacturer is calling out to seal that particular part. Gaskets create a seal between two stationary components, and seals create a seal between rotating parts. Because of the complexity of high-speed, value-driven manufacturing, the engineers have come up with a variety of different alloys. We have ferrous metals that contain some portions of iron, and non-ferrous metals that don't have iron at all. That would most likely be aluminum, brass, or stainless steel. It does not have any ferrous metals. Common metal for engine components is iron, is cast iron. There's several different alloys used for cast, gray cast iron for one. And there's also what's called compacted graphite iron, which has different additives in it. Steel has a wide range of alloys that come with different hardnesses that that are utilized in a softer metal is considered malleable. Showing here, higher carbon content is harder but more brittle. So when we get to tool steel, our typical mild steels will have what's called a Rockwell hardness in the 30s. We get to steel alloys, it's in the 40s, and we get Rockwells of 50, 60, and higher in tool steel, like our drill bits, our taps and dies, and other types of tooling. Steel is also heat treated and has a variety of alloy with the carbon content and other metals that are compatible to steel and will give us a steel alloy that'll perform as desired by engineers. Magnesium is very lightweight, but it has to be utilized as an alloy, typically in aluminum to keep weight considerations. Aluminum pistons in automotive are very common. Aluminum is very popular due to weight savings and also the fact that you can machine aluminum faster than steel. So the throughput for that manufacturing cell is much greater, and also the wear on the tools that do the machining, the mills, the end mills, and roll taps don't get the type of stress that they do when they're machining harder materials as like steel alloy. We have titanium, which is utilized in part in surfaces. We don't see large titanium parts in automotive or truck, but we see a lot of plastics, plastic and composites. Composite materials like the oil pans in engines have become composite. They're lightweight. And we see ceramics, coatings, and materials that are utilized in high heat applications. So ceramics can hold their geometry in high heat. Okay, here we're showing some exhaust manifold application, high heat application. And if a metal is ferrous, it has iron content. It's magnetic. Okay, casting. Metal is just heated to a liquid, poured into a mold, and the molds are often made using foundry, sand, and lost foam methods are the most popular high volume. And if you look, you see the seam in here. The seam is from a lost foam application, and it will actually look like styrofoam, the surface of the metal, if it's lost foam. And you'll see the seals from the castings. Okay, this manufacturing process is showing the side view of an engine block. Okay, forging. Forging actually takes the metal and pressurizes it and comes up with what's called a near net shape, so that there's only a small percentage of material is removed. In this case, with a crankshaft, the journals are going to be turned and machined until they have a very fine micro-inch finish. Pretty much a polished finish, and then of course they're going to be doing balancing and heat treating to the crankshaft. But the forging allows a much denser molecular structure and much more strength. In the case of a crankshaft, it's going to have longitudinal shape, but it's also going to be able to bend and work through the dynamic forces that are on it while the engine is running. Machining from solid billet. It's the strength between the cast and the forged part. It's in between, but it can also be made, machining can be made to extremely close tolerances today, utilizing today's machining centers that have very precise measurement and guidance and controllers for the machine tools. Stamping is done from sheet metal. It can be done from a mechanical process, but it can also be done with lasers and have less secondary operations with deburring and that sort of consideration. But stamping is typically high speed. It's relatively thin material. In automotive, it would be 10 gauge, which is less than 90 thousandths. Typically for external parts such as valve covers and oil pans are common stamp parts. Powdered metal is essentially melted powdered metal that goes into a mold, and it has a variety of alloys based on the application. Here we're showing connecting rods that are powdered metal, and these are not a cut, but these are basically a fracture fit that is very precise and has to be the parting line is very unique to each fracture, so you have to keep track of by marking or etching. You can't use any stamps, put numbered stamps on these powdered metal rods, they will crack. So you have to mark these as they come apart and make sure that you're match lining these perfectly, otherwise you'll have a unique problem with the engine. And the process of melting and pressing into shape is called sintering, and it's utilized today because it's a faster production process than having a forging and the machining that goes along with the bringing it down to the final part. Metal treatments, hardening is basically heated and cooled, has a fine grain structure, but it can become brittle. Tempering is moderate temperatures and then slowly cooled. It's a very controlled process to move a specific amount of air at a temperature over the metal as it is cooled down, so you get the hardness and less brittleness. Annealing is high temperature and slowly cooled. It reduces brittleness and allows the metal to be more manufacturable and machinable. So that's annealing. It essentially softens it but keeps the strength. Case hardening is an exterior process where your heat penetration is minimal so that we have the strength on the surface of the metal, if that's all that's required for that particular part. Ion nitrating uses gases and electrical current to alter the structure to increase the surface hardness. With shot peening is a blasting with small metal or glass balls. It creates miniature dents in the surface, and it actually is a form of stress relief, so that all the other processes in machining and forging put stress into the metal, and shot peening will reduce stress and remove stress from that part. Here we have cracks that can be caused by metal fatigue, stressing, extreme temperature, or lack of cooling, and manufacturing defects. If you have an air pocket in here called the void, and you have, like crankshafts will have a tremendous load on them, the torsional loads are huge on crankshafts, so you're going to have the braking occurring. And we have magnaflux or magnetic particle, and we have it only working on ferrous metal. So if the metal's magnetic, you can use magnetic particle to detect cracks. Magnetic fluorescence, they utilize a black light after they coat the metal, and they can see very clearly where the stresses and crack lines are. Dye penetrant can be utilized in any application as long as the surface is cleaned, and that aluminum is used in. It can also be used on clean on ferrous and non-ferrous metals. Pressure testing to see if there's any leakage in a casting, for example. Which part is cast or forged? The forged part has a wider casting line than a cast part. So the forged part comes out of what's called a near net forging die, and the metal is actually forced in. The casting line is much thinner, so that would be an example of how you can tell. Bolts, studs, screws, nuts, fasteners may be replaced due to manufacturer's recommendation or as a result of damage found during inspection. So you want to make sure that your fasteners are perfect for the application. Diameter, thread pitch, length, grade, and class is essentially the strength and the hardness. Washers, thread length. Here we have a shoulder or a shank here. We're going to find that there's a fillet. In some applications, it's very precise. That we have the head size. We may be using generic fasteners in some applications, and very specific fasteners that are OE engineered and designed for a specific application. Here we have a grade 5 because we're seeing the 3 hash marks on the bolt, and in metric we're going to have the number that'll give us the hardness. When a bolt length is considered from the bottom of the head from here to here, that is a bolt length. It does not include the head. Okay, so thread pitch is important, that we have a thread pitch gauge in our toolbox and we can quickly find the thread pitch. It'll narrow down exactly what that bolt is. But looking at the head is a good place to start also. Okay, yield. There's a certain amount of strength and clamping force when we do cylinder heads and we do torque critical components like connecting rod, bearing caps, main bearing caps, and cylinder heads. We have very precise amount of clamping forces required. And we also have one-time use bolts called torque to yield, have a specific value, and then they're turned a number of degrees. We use a angle gauge, or we mark the bolt to make sure we're putting the specified amount of angle on top of the specified amount of torque. Those bolts are typically one-time use in automotive because they stretch in order to deliver the clamping force that's required. Here they're visualizing being able to see if they can get the fastener to turn if it's frozen in there, and see if there's any possibility of getting it to turn with some shock. Now, we have to be careful here because it looks like the cylinder head or the block that it's in is high value, so we want to be careful that we don't damage the assembly trying to remove a fastener. This is a bolt extractor, an easy out, and I just love these names because it ain't coming out, so it's an easy out. But that's just a fun thing there. We have to be very careful that we drill the correct size hole for this easy out. So there's a corresponding drill bit number to utilize for that, and it tightens to the left. And it can be done with finesse. Once you learn the technique of using bolt extractors, you can remove some very difficult fasteners and get them out and save the part and the assembly that they're in. Okay, in utilizing our helicoil or utilizing a bolt extractors, it's a process. They're using the correct size hole here. You have to have enough material left on the side of the bolt for the extractor to work. Damaged threads can be utilized with, this is a thread chaser that will allow you to repair some damaged threads rather than using a tap, because these will actually put just enough cutting on it to clean it up so you could reuse it. Here we're utilizing this example is a helicoil. When you buy a helicoil kit, you get a special tap to put the inside threads into the damaged thread. You have to drill it a specific size, use a special tap, and the inside of the helicoil or the threaded insert will have the correct thread pitch that you need for the fastener. It takes some finesse to utilize the helicoil and how to dress the hole and get the part to start correctly without deforming the coil, and then knocking out the tang that's left on the bottom when you're done. They're not showing the tang here, but it is a process that we're going to do in shop and demonstrate. Okay. Gaskets are sealing two stationary parts. There's hard, soft, and there's also sealants. There's a variety of materials utilized with composite material. We used to have cork gaskets with rubber. Those were for head gaskets, not head gaskets, but valve cover gaskets. A variety of paper, rubber coated materials. But you have to use the correct gasket, and you want to save all your gaskets and O-rings that come out of the engine, and make sure that your kit that you have to rebuild the engine has the correct gaskets in it, not just size, but also material. There are instances where the gasket kits are shipped with either wrong or missing parts, so you want to make sure that you're checking all of these as you do your assembly. Sealants, liquid chemicals, RTV, which is your silicone base, and your anaerobics, which harden in the absence of air, are specified in certain applications. Okay, we're not going to get the video on this one, but here we're showing some half rounds that'll go into a valve cover to a cylinder head. Here we're showing an intake manifold and a seal, and we got some valve guide seals here are shown. Okay, this type of cylinder head gasket has to be able to withstand pressures and temperatures, and it has a stainless steel fire ring and elastometric sealing band so that this portion will seal around bolts or also passageways for coolant and oil. So they have a specific function if you see the elastometric bead. Some head gaskets have a time limit. On some of the Duramax diesel head gaskets, you have about 15 minutes to set it up. If you can't torque it within 15 minutes, you have to take it apart and do it again. So GM includes 2 gaskets for the Duramax cylinder head. Here's an example here showing your oil and coolant passages around the cylinder. This brand is Felpro. Felpro and Victor make a lot of gaskets for OEMs. And you're going to see the stains with the coolant. So you want to save your older gaskets, save everything that comes out of the engine, and match everything up and make sure it's perfect before you start putting things back together. They gotta match. That's what comes out of this. We lay them over each other and inspect the hole spacing and sizes, and you got some dowel pins and a variety of exact formations for your fire ring and your materials. If you have the wrong gasket, it could be the end of that engine. So you want to be very sure that you have the correct gaskets, especially for cylinder heads. Okay, so we're showing some V8 engine specifications here, showing the bore sizes and the piston size. So you're going to have a slightly smaller piston than bore, and they're showing a range. And you have to be careful with ranges, because if you're at the low end of the range, you may not be able to go to a cutting size. So when we have a 10 thousandths and a 10 thousandths bore, we can only clean up a 10 thousandths over bored out. We can only clean up a minimal amount of damage that's in the cylinder bore. So we have some guidance here showing us that they have a 10 thousandths oversize shown here, and you're going to have a range. So the range here is only 5/10 thousandths of an inch, which is a very minimal amount of wear. So when we have intake manifold gaskets, depending upon the manifold design, gasket may need to seal air, fuel, coolant, exhaust, and oil. So there's a lot going on in some intake manifold gaskets. And they may be a variety of materials. So you got steel, silicone bonded to steel, plastic, and or O-rings. So you have to pay attention to what's coming off the engine and make sure your replacement parts and your gasket kit, everything is exactly the same that came off that engine. Exhaust manifolds, extreme temperature. There's some thin metal is used in some applications. Gaskets may still be available for future service, but in the real world, we're going to be replacing anything that has been heated and cooled that many times. You're going to have to surface your the block side, and you want to surface your manifold side and make sure that everything has been cleaned and new hardware is installed. Hardware that's been heated and cooled many times is virtually non-serviceable. Okay, here we're showing valve cover gaskets. Common leak point due to wide bolt spacing and cover distortion. Everything heats up. Okay, gasket materials are used, but we require flat surfaces and proper torque specifications and torque pattern. Okay, same thing with oil pans. We have temperature. We got heat from the engine block, and we're showing a half round gasket going into the pan, and we're showing they may or may not specify any sealant. You have to be careful that you don't over torque, and in this situation you see the orange elastometric material on there, so when it's torqued correctly, that will compress against the flange of the engine block and correctly seal. So that's what you're seeing here in the bottom drawing. If that's torqued correctly with a crisscross pattern, the manufacturer calls that out in their service literature. Okay, miscellaneous gaskets, EGR valve, water pump, timing cover, manufacturer's recommendations, and check technical service bulletins. Technical service bulletins can give up a lot of information. When the manufacturer has a failure that occurred, and it occurred over a certain percentage of time, the technical service bulletin can nail the problem for you and bring you to a repair situation faster if it's a common failure. So you always want to check your TSBs and see if there's a common failure that's related to what you're working on. Seals. Rotating parts. Now, seal technology has advanced, and seal surfaces are striated in this crankshaft situation. They have striation, so a very small amount of oil is always on that sealing surface. You don't have the type of seals today that leave a ridge into hardened material. And also in some applications in high-valued engines, there's a wear sleeve that's on the nose of a crank, for example, and a very wide sealing surface so that there's constant lubrication and that the actual nose of the crankshaft has a wear sleeve that is replaced. So you do see some advancements in the application and the design of seals, so seals can last the life of the engine. So crankshafts and camshafts and water pumps and applications that have rotating parts are going to have seals, and you got to make sure that everything's clean and there's a coating of lube oil on that surface when you do your assembly. So we have a cross section here that shows a spring to keep radial tension on the sealing surface, a variety of lips. So if you have multiple lips, you have more surface area is being contacted to form the seal. Here they're showing a dust lip to keep out debris out of the sealing surface, and a garter spring, they're calling it in here, to keep the radial compaction onto that surface that you're doing the sealing on. Okay, they talk about repair sleeves are available for certain high-valued applications. There's also some machine shops are able, if you have a high-valued, say a crankshaft, and the nose has a groove in it, it's a high-valued crank or camshaft, or even a damaged journal. There are some specialty shops that can heat the crankshaft up to about half of the final heat treating temperature and spray on molten metal, cool that in a very controlled cooling application, and then grind it down to the original outside diameter that it came with. That is available in specialty shops, and it's only cost effective if you're utilizing it on a high-valued assembly. How to get seals out: you have to use a driver or an arbor in certain applications, and some you can use the little crow hook here and get them out. I do that really carefully, so I'm not this tip is not scratching anything and it's catching inside the seal surface. So you want to be careful and pry it in at least 3 locations so you can ease it out. The last thing you want to do is damage the assembly that it's coming out of. Sealants and adhesives, if they're called out, they're designed to be used. They form in-place gaskets, may be used in some applications, but it's based on manufacturer's recommendations. That is the key here. You never put anything in an engine that didn't come out of it, that wasn't called for by the manufacturer, period. Okay, some aerobic sealants are used, silicone-based, RTV, room temperature vulcanization. If it's called out, they're showing putting a bead of an aerobic sealant here. Okay, anaerobic hardens in the absence of air, but RTV hardens in air. So it needs air to cure. Okay, anaerobic, like Loctite, will harden in the absence of air. So when you put thread sealant on, either green, blue, or red Loctite, it'll harden in the absence of air. And you must pay attention because Loctite has strength ranges. It's got to be called out by the manufacturer. If you're using red Loctite and you have to get it out, you generally have to use heat to get it out. So just make sure that it's called out and their sensors safe, because you have oxygen sensors and you have mass airflow sensors that are expensive sensors, and they need to be utilizing the specified sealant. Which direction should the lip be facing? Now this is pretty straightforward, and the lip is always facing towards where it's holding the oil. So it's facing the fluid to be sealed. Okay, that wraps it up for this lecture here.